So Dr. Ashutosh Deepak Gore has 19 years of industry R&D experience. He joined Geo Platforms Limited in October 24, where he is working on next generation fixed wireless access technologies. Prior to Geo, he had been the technical manager of the WLAN 5 modeling group in Qualcomm Bangalore for 8 years. His team developed several key 5 hardware blocks across 3 generations of Wi-Fi chips. Before QC, he had worked in Samsung, Broadcom, Marvell, and Nortel networks. On the academic front, Dr. Gore obtained his BTech and PhD degrees from IIT Bombay and MS from University of Hawaii, all in electrical engineering. He has published 20 plus international papers and patents. Welcome, Dr. Ashutosh.
While they begin the system, just a quick show of hands. How many of you are students here? If you can please raise your hands. Wow. Okay, this is great. Faculty? First 2-3 rows. And from industry? Everybody in between. Okay, fine. So I have a task of keeping you all awake. Okay, and also you had a very sumptuous tea. So I'll make sure you get hungry before the lunch starts. Okay, that's my task today. Yeah. So hi everyone. So today what I'll do is I'll talk about a different topic. So I think we've covered a lot, by Professor Chokalingam on OTFS. Then we had very good talks on the next generation by Ashutosh and even by Anshuman. I'll take you to different worlds. So basically, this will talk about what is commonly known as Wi-Fi. So we call it Wi-Fi, we call it wireless LAN. They use the terms interchangeably. So let me get started. I had to put one disclaimer that since I'm from industry, whatever I'll talk about here is not at all trade secrets. You can easily get them from the internet. Books, papers, or any MATLAB code and all that. So let's come to what is the terminology here. So like I said, right, when we say wireless LAN or WLAN, these are usually standards from IEEE. So they will come under what is called at the study groups 2.11. When we say Wi-Fi, that usually comes in products or chip specifications because Wi-Fi is mainly meant for interoperability. So what happens is when you buy any product which is Wi-Fi certified, you will see that, Wi-Fi Alliance certified, and I will talk about a particular standard of IEEE. So just a little bit of nomenclature, I just want to get these clarified. Now, just like we have had generations in cellular, right from 1G to 6G, same way we've had actually 8 generations in Wi-Fi, which very few people know about. Now, the way I would say it is that Wi-Fi 1, or let's say Wi-Fi in general, has been there for 3 decades. It's almost been there for 30 years. So it began in the early 90s with Wi-Fi 1. That time we were using spread spectrum techniques. So we were using this direct sequence spread spectrum, complementary code keying. We used to get modest rates of about 2 or 11 Mbps, the peak physical layer rates. Later what happened is from Wi-Fi 3 onwards, there were standards called 11A and 11G. That's when Wi-Fi adopted OFDM, and that became a big game changer. So what happened is once we got into OFDM with 20 megahertz of signal bandwidth, with 64 QAM and with only SISO in those years, we reached 54 Mbps. Now imagine, you are somewhere in the mid or late 90s and you see devices, products with 54 Mbps speed. You would be totally bowled over, okay? After that, all the Wi-Fi generations, they began building up on different dimensions. So for example, when we went from Wi-Fi 3 to 4 or 11A to 11N, the biggest thing is MIMO, okay? We directly went from SISO to MIMO. We got almost a 4x increase, and we began doing single user transmit beamforming. As you can see, because of that, we went from 54 to 600 Mbps, almost 11x increase. So building upon the momentum of 11N, we went forward. So in the 5th generation called 11AC, we introduced downlink MU MIMO. I'll have a slide on this also in today's talk. And that is when we went from 4 streams to 8 streams, from 64 to 256 QAM, from 40 to 160 megahertz. So when you put all these multiplicative factors together, we went from 54 Mbps, from 600 Mbps to 7 Gbps. Again, almost like 11x increase. So as you can see, from 3rd to 4th to 5th, we got an order increase in the peak physical layer link rate. Then going forward, once we reached Wi-Fi 5th generation, then we had 6, 7, and 8, right? That's when we began actually getting inspired by cellular, by 4G and all that. Because 4G already had got uplink, they had got resource blocks. So you will see features like uplink MU MIMO, uplink OFDMA, and all those actually only give a modest increase, but point is that we began accommodating more number of users. So what was 4 users in the Wi-Fi 5 suddenly became 37 users in Wi-Fi 6. So we can have users with different QoS requirements, latency sensitive, and so on. Ultimately, what is currently in development in IEEE standards and many companies are interested is the 8th generation of Wi-Fi, which is called 11BN. It's in the works only. It will support up to 4K QAM, 4096 QAM, up to 8 streams. Promise is more than 30 Gbps for point-to-point. And it will have also 37 users with a lot of advancements in MAC layer. So as you can see, Wi-Fi has been modestly working in the background. Okay, we are already at the 8th generation. Okay, you see it here, somewhere here, and you'll see it all over your campuses, your homes, your offices, and all that. Okay, and we kept pushing the envelope. Okay, on the QAM, on the bandwidth, on the features that you have in downlink coupling, going to OFDMA, and so on. So with this as the background, I will then focus now in the rest of my talk on the physical layer evolution of Wi-Fi, okay, or WLAN. Let's go on, okay. I want to spend a couple of minutes on this slide because this is something which is normally not taught in academia, because I also was sitting in one of those back rows 20 years back. And this is something which I want to tell, having been in industry for, about 19 years, right? So what happens is, let us look at how the physical layer of wireless LAN, or even for that matter, cellular, is structured. Make it very simple, point to point. So what we'll do is initially we get bits from MAC, which is layer 2, right? We will do encoding, we'll do modulation, we'll put it in some QAM plane. Then there'll be a couple of more blocks, and then because we are using OFDM systems, we'll be using an IFFT, okay? Post the IFFT, we'll then send a couple of more blocks, it will go to the DAC. Now what the DAC does is that it will take a digital signal, okay, which will be quantized in amplitude and it is sampled in time, into an analog signal. So that will be continuous in amplitude and continuous in time. Okay. So this DAC does a wonderful job there. Then there are a couple of more blocks, and then we go to this frequency upconvert, which is also called as mixer. So that's why you see here this e power j omega txt. This is where it goes from the baseband domain to the RF domain. Then MIMO is very common. I have just shown a very, very common application where you will have 4 transmit chains, which can happen in an access point, which is there usually in campuses and homes. And you will then send it over a MIMO channel, and there'll be 4 receivers. I'll come to the red blocks later. At the receiver, we'll add this AWGN. Then there is a frequency down converting mixer. Go forward, there is ADC. ADC will do the exact reverse operation of a DAC. It will take a continuous time, continuous amplitude signal, and they make it discrete time and discrete amplitude. Then onto the FFT, and then onto the demoted and decoder. So what happens is that what this particular block shows now is like the skeleton or the major blocks, which must be a part of every MIMO OFDM system. Before I go into the impairments, which is the bottom part of this slide, I want to talk about a couple of definitions. These are very important. So what happens is that, as you can see here, there are 3 layers. Okay. One layer is that when you are in the baseband. So until the frequency upconverter, you are in the baseband, that is BB. Then between the upconverter and downconverter, including the channel, you are in the RF domain. It's in the passband signal. And then again the baseband domain. So there is a baseband RF, there are 2 boundaries. Let's go one step ahead. Before the DAC, you are in the digital domain. After the ADC, you are in the digital domain. Okay, between that, you are continuous time, so it is analog. One step further, before the IFFT, you are in the FD, which is called as frequency domain. From the IFFT all the way up to the FFT, you are in the time domain, which is TD, because the channel in reality is always time domain. Then after the IFFT, you are in fixed domain. So what happens is that there are so many combinations. You can have digital baseband, analog baseband, RF analog, RXFD, TXFD, and all that. And literally speaking, now, for those of you who are keen on working in hardware, especially physical layer, right? You can practically find carriers in all of these. You can be an expert in RF analog design. You can be an expert in digital baseband design. You can be an expert in mixed signal design, and so on and so forth, right? So this pretty much gives you a career chart for those who want to work in semiconductor industry and physical layer. Okay. Now, again, what is not taught in academia is what are the impairments. Okay. So I have just given about 5 of them here. I think there is some color thing, but don't worry about that part, right? So naturally, we all know as communication engineers that there are some necessary evils. Okay. And the most necessary evil is what you add at the receiver here called as additive white Gaussian noise. Okay. I'm sure all of you have done in the courses, you cracked your A grades and all that, right? There are a couple of more things to hurdle over before you crack the next grade. Okay. One thing is the transmit EVM. I think Anshuman, Ashutosh talked about this power amplifier, right? So what happens is that because you go about doing the signal processing on the transmit path, you do upsampling, filtering, so many operations, there are nonlinear components, right? Ultimately, you get some kind of a ball around the concentration point before even adding the white Gaussian noise, before you send over the channel. That is the transmit EVM. Okay. This happens because you have to send it over the air and there is a practical electronics. At the receiver, I already mentioned you have got AWGN. Now, very interestingly, at the mixer, there is an impairment called as carrier frequency offset or CFO. Now, the CFO is given the formula here, that is FRX minus FTX. You may say, what's the big deal? It's always zero. No, it's not zero. It could so happen that a transmitter is from company 1 and the receiver is from company 2. Okay, so their crystals, their LOs and all that will be a little bit different. So this value can be of the order of a few hundreds or a few tens of hertz. Okay, this has to be estimated and compensated. So we have CFO estimation, CFO compensation after that. Okay, similarly, the sampling at the ADC, the sampling rate at the ADC can be different from the DAC interpolation rate. Okay, so this F samp ADC minus F interp DAC also needs to be estimated and compensated. Okay, so SFO, CFO are necessary evils in any Wi-Fi hardware, even in cellular, which unless you compensate properly, you will not get a good performance at the physical layer. Okay. Then I already spoke about transmit EVM. AWGN, I think all of you know very well. As you know that AWGN has its roots in KTB, where K is the Boltzmann constant, T is your absolute temperature, and B is your bandwidth, right? Okay. Unless you happen to be at 0 Kelvin, you have to have AWGN. Noise figure, okay. This is very interesting. So noise figure is something which you add as extra noise over and above AWGN, okay. It comes from the RF chip, whatever is shown here and here. And because many of these RF components are non-linear, okay, to enable their operation in the analog domain. So what happens is that wireless LAN physical layer entails modeling all this. It can be in MATLAB, it can be in C++, modeling all these impairments, developing the algorithms, developing them in fixed point engineering, and being able to have good reference models in C++, and later in RTL, VHDL, if you happen to be a hardware engineer, okay. So this pretty much, is the one-pager or executive summary of the wireless LAN physical layer. Let me go ahead. Okay. Now, since the talk was focusing more on the evolution of Wi-Fi or the physical layer, I want to talk about some of the key pillars. Okay. They happen to be OFDM, bandwidth, higher order MCS, MIMO, DLMU MIMO, and some miscellaneous parts. I will just touch upon each of these in about 2 minutes each so that you will get a flavor of what I'm talking about and how they have evolved, okay, organically over the Wi-Fi standards. Let's start. OFDM is mostly textbook material. I'm sure all of you have learned it in your dual degree, MTech, PhD courses, but just a quick overview. It's by far, I believe, the best file modulation technique that's implemented in hardware. Okay, again, this is based on use cases of Wi-Fi. I can't generalize to bullet trains and I can't generalize to LEOs. Okay, surely OTFS has a lot of potential. It will happen. Definitely, but OFDM, because of its maturity of, like I said, over 3 decades, there have been very, very efficient hardware implementations of IFFT and IFFT. Because of that, we could scale from 20 megahertz in the first generation of Wi-Fi, that Wi-Fi 3 actually, to 320 megahertz in the later generation, right? So OFDM was being able to scale in bandwidth and hardware very easily. Like I mentioned, it has been around for almost 25 plus years, okay, and it is still surviving. Now let's look at what happened in the other worlds, right? For example, in the cellular world, we had OFDM adopted from 4G LTE onwards, okay, for about the last 10, 12 years and all that. And it's also there in 5G and in 6G. Very interestingly, when you come to the wired world, right, especially in Western countries like USA, there is this thing called CMTS, Cable Modem Termination Service. They use that for accessing their channels and all that, the serials and all that. So even here, OFDM has been there right from DOCSIS 3.0. Okay, so it's there in the wireless world, it's there in the wired world, across 3 standards. Competitors wise, and of course I read papers on this and I'm also follow what's happened in academia. NOVA definitely had a lot of potential. I think this came about a decade back or something, but unfortunately it has not been very good in hardware implementation. And just like how Professor Chokalingam mentioned today, OTFS, yes, it is going to happen in hardware, okay. But I just put a little bit of a diplomatic thing. Let's see how it fares in the coming years, okay. So hopefully it's there in academia, MATLAB, C++, hardware, and be there after 1 decade, okay. Now a slight price to pay, like how we all have to pay GST and income tax, right? One small income tax about OFDM is that is cyclic prefix, okay. It takes about 20%, 10% of your overall physical layer time, small price to pay. Because ultimately, because of the CP, you can have single tap channel equalization. And this is the biggest selling point of OFDM, which is why 4G took it in cellular and 3G did not have it. They had an adaptive channel equalizer. It went more and more longer, higher number of taps as the channel delay spread increased. Okay. So that's a quick primer on OFDM. Let's come to bandwidth, right? So bandwidth and OFDM, they go hand in hand. Okay? They're like 2 buddies, right? So usually this always works. Bandwidth expansion. Like I said, you can go from 20 all the way to 320 megahertz. However, what happens is that ultimately who decides how much bandwidth? It is the company's telecom regulatory authority, the TRAI that we have in India, right? Okay. So since Wi-Fi operates in the unlicensed bands, so we do have 320 megahertz, but it's not yet approved, okay, in India, okay. So if they approve it, it's good. One thing I did read about the news was that they did allow 6 gigahertz band, the Indian authorities, in this particular range between 592 megahertz for low power indoor, very low power indoor, and very low power outdoor wireless access. Okay, this happened, I think, 3 months back. And hopefully, with the 6G band opening up for unlicensed use in India, we will have more and more players and more applications, okay, where they will adopt the 320 megahertz channel, which was there from the Wi-Fi 6 onwards. Now let's come to one thing I mentioned about this concept, TX EVM, right? So as you are aware, that we have this thing called MCS, Modulation and Coding Scheme, which is there in all the wireless cellular and Wi-Fi standards. What I've shown here is that there is a 16-QAM constellation, which is typically MCS 3 and 4. And before you even send it over the antenna, we have this thing called TX EVM ball. Root cause, nonlinearities, upsampling, filtering that we have in the transmit path. So now what happens is that we do accrue this EVM ball all the way from TXFD to RXFD. Okay. Now you say that, no, I want to make this more dense. Why 16? I'm not happy with 16. I'll go to 256, 1K, 4K, 16K perhaps, right? But the ball size will not change automatically. You have to have better and better hardware design. You have to have better and better RFIC design, analog design. So what happens is, I'll give an example. Suppose in Wi-Fi 7, right, we have this 11B, it supports MCS 13, where we have 4K QAM with LDBC code rate 5/6. Here the requirement set by the standard is minus 38 dB of transmit EVM. Okay. Naturally, this ball becomes bigger and bigger as you go on the receive path and other impairments that you have the receiver, right? Okay. So the long story short is that the quality of your analog and the RF design, that is what determines your EVM. Okay. Not some other magic. Now, as an example, suppose we want to support 16K QAM, which will happen, say, after a couple of years. It may happen in Wi-Fi 9, for example, right? That time we have to have 3 dB more stringent EVM for this compared to 4K QAM. Okay. So here what will happen is that it's not just a matter of beating this number, doing the circuit design, and what happens in the hardware world is that you want to be able to support this over variations in TVT. So this P called parts. You send to a foundry, you get different parts. You have statistical variation, right? So parts, voltage and temperature. Okay. Across all these variations, you must support minus 41 dB EVM, which is again a very, very challenging thing from an engineering point of view, right? So this is how basically is the higher order MCS story. So long story short, yes, we can support 16K QAM in the future standard, provided your hardware analog supports it. Now, this is again a little bit more of a textbook material. Here what happens is we have MIMO, which I think all of you are aware, those who are doing master's PhD, right? So here what happens is, I want to just tell you a little bit of a taxonomy. So we start with the MIMO equalizer, which is a must-have whenever you have multiple stream communication. There are two types of it. There's linear and there's non-linear. In linear, you can go to zero forcing, this is the equation. Your equation is the usual y is equal to hx plus n. And in MMSC, you have an additional term called n naught I. If you go non-linear, then you have to go to maximum likelihood, where we find out the argmin. Now let me compare all three equalizers, ZF, MMSC and ML, from the point of view of hardware. So zero forcing has got least area. The problem is that whenever you have a channel deep fade, that time the noise will be accentuated, okay, which can happen, for example, when you have low SNR. So that is why it performs very low compared to ML and MMSC, and it's also a little bit sensitive to what is called as interstream interference. So that is why, though zero forcing is very, very efficient in hardware, it will not work under low SNR scenarios, okay, for when you want high range, for example. Now we come to MMSC. One good thing about MMSC is that we have taken this noise power into account. So it's slightly better than zero forcing, slightly higher area, and some companies use it whenever they have this, beam for me in downlink MU-MIMO. They can use it in that. ML is by far the best in the following sense. Okay, what happens with ML is that you want to use it because it gives the best performance. In terms of dB, we can sometimes get 1.52 dB better than zero forcing. Okay, the problem is that it scales with the number of special streams. So for example, if you take one stream, it's very easy to put ML. If you go for 4 streams, it can be very high. Now, naturally, engineers and researchers, they have come up with very, very optimized schemes for 2 streams. So for example, for 2 streams, you can even search on Google Parents, you will get optimal equations, optimal hardware implementations, right? But when you go to 3 and 4 streams, you have to go for suboptimal, do something called subset pruning and so on and so forth. So this is pretty much how the equalizers stack when it comes to MIMO communications. So what a particular chip vendor will choose, say for example, Qualcomm, Marvell, MediaTek, etc. It depends on what the particular application is and the use case. Let me come to one more interesting topic, which is downlink MU-MIMO. So if you can see this figure, I hope it's a bit visible, or sorry, is there a way to zoom this? Any of the organizers? Okay, fine. I'll just use my laser pointer. So what happens here is that we have an access point and we have got two stations. So note one thing, what happens in downlink MIMO compared to what I showed previously, the SU MIMO, is that in a single shot, this access point of the beamformer wants to send data to two stations simultaneously. So usually when we say MIMO, it only is point to point. It is between one AP and one state. So here, as you can see, it is sending two streams, SS1, SS2 to the first station and SS3, SS4 to the second station. There are three stages: sounding for channel estimates, compressed beamforming feedback, and pre-coding. Okay. And I'm sure all of you who are doing master's, PhD, you'll understand this equation very, very easily. So what happens is the equation that you get, okay, this Y vector will be this block matrix V into the X vector plus the noise vector. Okay. Now, if you want the best performance from downlink MIMO, you want the off diagonal matrices to be almost zero. Point is that how can you guarantee it, right? Now, that is where I want to talk about what is in the bullets, right? So I already mentioned about the first bullet. Now, if you come to DL MIMO, the performance that you get now, it is very, very sensitive to where those two stations are located with respect to the access point. So here, of course, I have shown that they are a little bit far apart. So it may very well happen that this channel and this channel, the two H matrices now, the 2 by 2 matrices, they'll be little different. Okay, what does different mean in mathematical terms, right? Okay. So imagine, for example, that you want to find out the separation between the two matrices. Okay. Suppose you can put them in some vector space. How far are they? What is their distance norm and all that, right? So if you have got a sufficient separation between these downlink channel estimates, only then, and if and only if, that is the time when downlink MIMO will work properly. Okay. If it so happens that these two stations happen to be in physical proximity of each other, then it will not work properly. So there are only certain favorable conditions under which these DLMU MIMO, pre-coding based MIMO, will work properly. So what happens is that when do we kind of use this, right? So here, I want to talk about a little bit about AI here. Now, suppose we make this not 2, but 3 or 4 stations, okay? So what will happen is that more than, for example, finding out the faraway locations, say that there are many stations and we want to put them in pairs, like 1, 2, 3, 4, etc., right? So ultimately, can we pair these stations appropriately when there are a large number of users, so that we can do downlink MIMO along with user grouping and downlink scheduling as a joint problem in optimization. Naturally, this is a very, very rich ground for using AI ML techniques, whatever you kind of want to use. Now, there are 2, 3 more fancy things I want to talk about. Wi-Fi 6 onwards, 11x onwards, has something called OFDMA. Okay. So here, basically, the idea is that instead of being only in a certain small set of bandwidths like 20, 40, etc., we went to fractional bandwidths. Okay. So it was called a resource unit. So we had 2, 5, 10 megahertz and all that, right? And then later, this actually helped to increase the number of users to 37. But then when we went to Wi-Fi 7, right, we could basically combine 2 RUs. So we had something called RU78. Wi-Fi 8 had got something called discontiguous RU, because here what happens is that instead of keeping all the tones together, we kept them spaced. So when you have a channel which is selective in frequency, they can be more resilient to deep fades than if you have continuous. So this is doing good. It can give half to 1 dB, but nothing great. So that's why nothing very fancy here. LTPC, the same thing. So what happens with LTPC is that it can do much better than BCC, especially when you have got delay spread channels. Indoor channels are inherently delay spread. So here what happens is that sometimes you can get half to 1.5 dB improvement compared to BCC, especially because indoor channels happen to be delay spread. But theoretically, there are papers which show that it is almost within 0.1 dB of the Shannon limit. So LTPC is by far the best encoding decoding scheme. Again, here in R&D, not much, except that you can make the code size longer and longer. Okay, and then you can keep improving whatever is implementation. For example, people use something called LBP, layered belief propagation, for LTPC decoding. So what happened is, in the last couple of minutes, I've just covered the main pillars, right? Now, let me just throw open maybe 1 or 2 research problems, because I see a good number of students here. Okay. Now, I talked about ML, right? So what happens with ML is that, if I just go back to the slide very, very briefly, it's difficult to scale downlink MIMO beyond 2 stations, because what happens is that with 2 stations, you want their channel matrices to be in different points in the vector space. Imagine 3, okay? You're throwing something in the sky and you want them 3 to be very, very far apart. It's more difficult. So difficult to scale beyond 2 states, and when the number of streams is more than 4. Just keep this in mind when I go to this particular research problem, okay? So the idea is that, can we think of having a 8 ml MIMO equalizer? So for example, the standards definitely support 8 streams in MIMO, okay? Now, let us say that for whatever is Wi-Fi 8 and beyond, we want to have an equalizer, basically this RxFD MIMO ML equalizer for 8 streams under the following terms and conditions. The first is make it hardware efficient. Okay. See, we can do anything in paper or we can do something in MATLAB and make it work, right? But for example, can it be implemented in hardware with some reasonable area and with not very high latencies, right? Secondly, perform well both over indoor channels, which are typically called as DN loss in Wi-Fi world, or even fixed wireless outdoor channels. Okay. And finally, we want the gap from the optimal ML, okay, which is the brute force ML, which does exponential search, to be less than 1 dB. If you can ask me, this particular problem itself is so challenging. You can have a couple of PhDs work on this, okay, trying to make this work in hardware. Something more interesting than this, okay. I think even the previous speakers, Ashutosh and Anshuman, talked about convergence, right? What we are looking at is in Wi-Fi, can we have convergence in the unlicensed band, which is sub 7 gigahertz? Because there are 3 bands where Wi-Fi works: 2.4 gigahertz, 5 gigahertz, and 6, right? So these bands are called as sub 7 gigahertz collectively, and which is what the current standards are. Then millimeter wave Wi-Fi, there are other standards. There's 11AD, 11AY, right? Why can't we have convergence in both of this? Okay, there are use cases. For example, we can have a common packet structure for both sub 7 and millimeter wave Wi-Fi. We can have tri-band MLO. What tri-band MLO means is that you want to send simultaneously over 2.4 gigahertz, 5.6 gigahertz, and even, for example, you want to send over 45 gigahertz, right? That will be very, very challenging from the point of view of hardware design and even the packet format definition. Okay. Joint baseband IC, RF hardware, and millimeter wave antenna design to be able to support both. You can even come up with these schemes where maybe only one of them is a control channel and the remaining are for data. There are so many things which can innovate on this part. And finally, optimize the performance of this for indoor as well as low mobility outdoor channels. Wi-Fi, because of its very nature, is not designed for Doppler. It's not designed even for the speeds that you have in typical vehicles, right? But for pedestrian velocities and for indoor channels, it works beautifully well. Okay, and that's what has made Wi-Fi, very ubiquitous. Okay. So I will stop here. I hope this was a good, pedagogic lecture for all of you. Okay, and these are the references, and wish you a very happy birthday to Mr. Chaturvedi. Okay, thanks for inviting me here.
We have time for a couple of quick questions. And I will make a small comment that we do teach carrier frequency offset estimation and then sampling frequency and phase estimation, at least to our BTech students. And if some of them are there, they'll be excited to hear that it is very practically useful and they'll have a lot of job opportunities if they learn it properly.
Great to know that. Thank you, sir.
And I will have one comment. This is what it is, elections. I was to work with currently as latest last week is you can use for indoor fixed wireless channel, $0 with high real spreads. In this we have and echo will come far from the other end of the wall and then come back and we may exceed more than the cycle that is doing right now.
Okay.
So there again, 2 liters is possible with that test. The more recent papers that have been uploaded in market talks about that test over cycle physics So that is a special case where you have a period to take out of the tau-t. To bring it to the minimum, it collapses to OFD in some form. But if you use that space, minimum period, it performs better than OFD itself with single tap equivalence.
Okay.
That should not be treated as complex technique. It is a special case where single tap equalizer, like OFD is possible in the data. You do a fixed resolution based recorder without channel knowledge of the transmission. So everything falls into place, and that is better than OFD. It's single tap equalizer. And that I think is state of the art. That is for information.
Okay, that's great to know.
Period of time, as we said, let's see what a period of time.
Yeah.
Scale. I think for Wi-Fi, OTFS is a good candidate to consider. Not do it very long, but that is a clear case. But as a special case, even for indoor Wi-Fi or even cellular in those communities, is a good candidate.
Okay. Sure, sure.
With it and test it and validate it. That takes about 5 years. So that's a good way.
Thank you for the information.
Ketan.
Yeah, very nice talk. Yeah.
Oh, okay.
Very nice talk. Nice to hear about the blue LAN because rarely there are very few talks on that topic.
Yeah.
I want to ask your opinion about long range Wi-Fi.
Yeah.
There's a particular standard in that, and I'll just tell for the benefit of others, you may not be aware, there is a interesting use case of Wi-Fi which is for UAV communication. Even with directional antenna or with a directional antenna, you can get something like 3, 4, 5 kilometers of range, following all the power limits that are set by government. And also the UAVs can communicate with each other over 1 or 2 kilometers range easily, because in outdoor you have very good line of sight and UAVs are not really that fast.
Yeah.
So,
Okay, so this is a very interesting topic. We'll talk offline after this thing, okay? Because there are some company IPs involved here. What I will just say is that, see, Wi-Fi, number one, can be used for low mobility. Number two, it can be used for long range. And it can be used even at higher frequencies, okay? It's a matter of how you currently tweak your link budget. Ultimately, that's what it boils down to, right? So if you want to increase your range, you can start using phased arrays at both transmit receive. You can use parabolic dish antennas, right? That's one way of doing it. If there is mobility, like how Professor Ketan mentioned, of UAVs and all that, they're within the limits of pedestrian velocity. Yes, definitely you can also kind of use it there. You can even tweak the MAC layer protocols, okay, to be able to achieve this. There are even some standards. I think there's something called 11P for long range Wi-Fi, which has to be done. So what I think is that initially start with the use case, come up with what the requirements are, then see, for example, whether you need to actually use a current standard or modify an existing standard. But as we speak, right, Wi-Fi not only is getting into IoT, just to give an example, right? For example, Wi-Fi can also come in the next earbuds, the next generation earbuds, right? Wi-Fi can even go long range, okay? And little bit of low mobility scenarios with help from OTFS, as Professor Chokalingam mentioned, right? There are multiple topics there. We'll discuss more during the lunch break. Yeah.
I'll add to it. So there is some work which is done for extending the Wi-Fi. It's called Wi-Fi rural extension. So basically, physical layer will work, but you'll have to extend. I mean, you'll have to tweak the MAC layer so that you can do it for a longer range. So you can. I think that work was done probably 1.5 decades ago. So before
IT Kanpur only that was.
Okay, I think it was joint work somehow. So, okay, thank you, Ashutosh. So, can I request Professor Chaturvedi to express our gratitude to Dr. Ashutosh for the excellent talk he has given by presenting him a small memento.
Correct.
Okay.
Thank you for the opportunity.